Hello. Here we'll talk about the generalization of Fermat's little theorem, which belongs to Euler. And as Fermat's little theorem, it says something about powers, but now powers modulo any modulus. So let's choose such modulus n and introduce what is called the Euler's function. So the Euler's function on n counts how many invertible integers mod n there are. And invertible integers mod n, and the multiplication of course, are classes of those integers. Well, if I want to count, I want to have them finite, and then I have to look at their congruent classes. So those invertible, I keep only, and they are, we can just count the natural numbers less than n, which are coprime to n. That is the condition equivalent to invertibility of the congruent class. So that's what we're counting. We're counting the numbers, natural numbers less than n, which are coprime to n. The two basic facts which allow to compute Euler's function on any n. So the first is the multiplicativity property. We have Euler's function on a product equal to the product of values only if and only if m is coprime to n. And that follows from basically the Chinese remainder theorem. Right? We have to compare integers mod a product of two coprime things with integers mod factors. So theoretically, you can frame it as an isomorphism, as a bijection between congruent classes mod m times n and pairs of congruent classes mod m and mod n. And this bijection preserves addition, and it is also preserves multiplication, because what we really do is just take a congruent class and assign to it a pair of congruent classes of the same number. This map is well defined, doesn't depend on what number we really take in a congruent class, and it is a bijection. And obviously it is multiplicative, and so it gives us a bijection between invertible integers mod mn and pairs of invertible integers mod m and n correspondingly. So counting this is as good as counting pairs in those, and that's why the formula. But it only works when m and n are coprime to each other, so that's why we have this condition in place. The second allows to compute Euler's function on powers of primes. So here p is a prime. Note that this allows to reduce any computation of Euler's function on any number down to powers of primes. And for powers of primes, here is the answer. It is p minus 1 times p to the l to the power l minus 1. And that again is from the simple logic. We are counting things which are coprime to p to the l. Well, it's easier to describe those which are not coprime to p to the l. They will be multiples of p. And so to count those which are coprime, it's enough to count those which are not and take this number out. And it is easy to convince yourself that the number of things which are multiples of p will be p to the l minus 1, will be this number. And so we're taking total number of congruent classes, which is p to the l, and subtracting p to the l minus 1, hence this answer. So now we know how to compute Euler's function on any number, and let's put it in use. Let's put this Euler's function in use. Here's this Euler's theorem, which says that if we start with something which is invertible, so some integer which is co-prime to n, then its power, which is this Euler's value, will be congruent to 1 mod n. So I'll give a proof. Well, it will be really a delegation to some fact from group theory, some basic fact from group theory, which would just be this Lagrange's theorem. Which says that if we take a group element in any finite group, then the power of this element, the power which is the order of the group, will be the trivial element. So then we just take this group and have this result. Let me finish by showing how Euler's theorem generalizes Fermat's theorem. So here's a corollary, which is Fermat's little theorem. Well, which says there are two versions, but one version says that anything which is not divisible by p, coprime to p, raised to the power p minus 1 is congruent to 1 mod p. And it's just because it follows from Euler's theorem, because by this rule Euler's value on the prime is prime minus 1. Will be more with applications of Euler's theorem, so stay tuned.